Okay, let us start. Could you please confirm once that I am audible, visible, as well as you can see this presentation? Could you please confirm once that I am audible, visible? Okay. Okay, let me just begin. So, very good afternoon, everyone. My name is Ambuj. I am a research scholar at Agriculture and Food Engineering Department from IIT Kharagpur, and I will be taking your live interactive session for the course Computer Vision. This course is taught by Professor Jayant Mukhopadhyay from IIT Kharagpur, and what we will be doing, we will be solving some of the questions based on previous week's content. Okay, some of the objective type questions based on the previous week's content we will be solving. And one of my sincere requests to you is that please take up pen and notebook and please try to at least jot down what are the basic questions that are being asked. Okay, what are the concepts and how I am dealing with it, and similar methodology you can also use to solve these type of questions in the examination. Okay, so very first question for the present session is this one. Given two features, each of size 4, s f equal to 4124 and g equal to 9122. Now you have to compute the normalized cross correlation and cosine similarity. Okay, that you try to compute. Okay, options have been given. Try to jot it down, then I'll tell you how to compute this particular problem. Okay, try to at least jot down what is f, what is g, and now we'll calculate the normalized cross correlation and cosine similarity. We'll try to compute that. Okay, so I hope you must have noted down f and g. Now you just see the procedure here. Correct solution would be B. Okay, 0.4725 and 0.849. Okay, first of all, you try to understand that there is a term which is ZNCC, zero mean normalized cross correlation. Okay, that particular thing. Okay, first of all, our basic intention should be why we are going into this cross correlation analysis. Okay, we are going in this particular analysis because we want to establish relationships between different input images that have been provided to us. Okay, so if we want to establish any particular relationship between number of pixels which are there in an input image, okay, then we have to perform some type of statistical analysis. On the basis of that only, we will be able to predict whether that particular shape or that particular geometry falls within a certain pattern, or we are able to deduce some kind of meaningful information from the given image. Okay, so that is the particular intention, that is the particular purpose why we are going into the statistical analysis. Okay, and one of the basic statistical analysis which you can see here is ZNCC, zero mean normalized cross correlation. Okay, which is defined as 1 upon n. Okay, summation I equal to 1 to n fi minus f bar, gi minus g bar, and then sigma f sigma g. Okay, first of all, you have to understand what is f bar. F bar will be nothing but in simple terms it would be mean. Okay, this particular term would be mean, both the terms. Then sigma f. Okay, sigma is nothing but your standard deviation. You just try to calculate using the requisite formula. Okay, 1 upon n minus 1 summation fi minus f bar whole square. Okay, this is your sigma f. Then you try to calculate the value of sigma g, which is 1 upon n minus 1 summation gi minus g bar whole square. Okay, these two particular terms are there. You try to compute them. Okay, now if you try to rigorously calculate what is mean is nothing but your f bar. F bar would be 4 plus 1 plus 2 plus 4 divided by 4. 4 plus 1 is 5, 5 to 7, 7 4 is 11, 11 by 4 is 2.75. So f bar just we have calculated. Then g bar will calculate 9 plus 1 plus 2 over 4. 9 plus 1 is 10, 10 plus 4 is 14 by 4, that is 3.5. Okay. So f bar and g bar, the first two terms we have calculated. Okay. Just we have to compute sigma f and sigma g. Okay. So for calculating sigma f and sigma g, it is the better approach which you can take in the examination is using a tabular notation. Okay. Why tabular notation? My dear, please try to understand that the points are maybe up to 10 also. Okay. So if you will not track that in which direction you are going and in which direction you are calculating things, okay, then certainly the things may go out of your hand. Okay. So that is the reason. Okay, 1, 2, 3, 4, 4 points we have seen. The 5, 4, 1, 2, 4 that we have seen. Okay, now we have to calculate fi minus f bar. Okay, so that particular thing we will try to calculate. Then square of that we'll calculate in column number 4. Okay, similar to that for GI is 9122. So similar to that, GI minus G bar and GI minus G bar whole square. Okay, so sigma f in the direct denomination would be nothing but sum of all these fi minus f bar whole square. Okay, that summation 1 upon n multiplication of that and under root of that. Okay, so sigma f, if you will try to calculate, it will come around 1.5, and sigma g, if you will try to calculate, it will come around 3.6968. Okay, so sigma f, sigma g already calculated. Okay, now nothing is left. Okay, one another term is left. Okay, which is this particular term, the numerator part. Okay, that denominator part you already have calculated, sigma f, sigma g calculated. Just one another term is left, that is this particular numerator one. Okay, so that numerator we'll try to just calculate. Okay, that is only left. So numerator part would be nothing but summation I equal to 1 to 4 fi minus f bar gi minus g bar. Okay. So that particular term you try to just calculate. There is nothing which is new to you. Okay. All the terms are there. Fi minus f bar means product of these two particular columns. Okay. First column is this one. Second column is this one. Okay. So it will be 1.25 multiplied by 5.5. That computes our first term. Then minus 1.75 multiplied by minus 2.5. That computes our second term. And plus and so on up to the last or the fourth term. Okay. So that will come around 10.5. Okay. The product of these two particular columns. Okay. Just 1 second. Product of fi minus f bar and gi minus g bar. Okay. Next is you try to compute the average. Okay, means divided by 4. Okay, 10.50 that will value will obtain. Then you divide it by 4, it will be 2.625. Then Z and CC value would be 2.625 divided by 1.5 multiplied by 3.6968, that is 0.475. Okay, this marks the end, okay, of the first part of the question. 0.4725, that value I am getting for Z and CC, normalized cross correlation. Okay, so if I am able to compute this particular information only, hereby I can eliminate all the options. Okay, and the correct option would be my second one, 0.4725. Okay. Then cosine similarity is there, cos theta equal to f dot g over mod f mod g. Okay. This is the cosine similarity. Already I have taught you this particular concept in, I think, week number 3. Okay. Very, very important concept of vector algebra. Okay. If you have to calculate the angle between two particular vectors, then there is no shortcut method. There is no direct method except of this. Okay. So this is the direct and most relevant method. Other methods are also there, but they would be bit too hazy. Okay, so directly you have to just compute the dot product. Okay, dot product of the respective components that you will try to calculate here. Okay, f dot g you try to calculate, it would be around 49. Okay, mod f is nothing but under root of square sum of all squares of all the components. Okay, mod means modulus. Okay, or the length of that particular vector. Okay, so that you try to compute. It is a four-dimensional vector. Okay, you try to compute that, it would be 6.082. Then mod of g. Okay, length of the vector g you try to calculate. And double mod is there means, first of all, the double mod is there means, even though it can come negative, but still you have to take the only the positive value. That is the reason. Okay, so that would be more g, length of the vector g would be 9.487. Okay, cos theta, if you will try to compute, it would be around 0.849. Okay, cosine similarity is nothing but the angle between vectors f and vector g. Okay, so that if you will try to compute, it would be 0.849. Okay, so correct option would be option number B only, that we already have seen. Okay,
మధ్యాహ్నం వేసుకునే టాబ్లెట్స్ నేర్చుకున్నా
just give me a second. Yes, that we already have seen. Okay, the ZNCC part seen in the first part of the question, it was coming around 0.4725, and now the cosine similarity also we have computed, it is 0.849. Okay, so both of the things we have computed. Okay, yeah. So both the normalized cross correlation, okay, NCC, as well as the both of the terms which are normalized cross correlation as well as zero mean normalized cross correlation. Okay, or ZNCC, they aim to measure the key similarity between two signals. Okay, two signals. Signals means in image processing, or in your signal processing, every information, every bit that is dealt in as a signal. Okay, so both of the inputs, okay, they are dealt either as a signal, okay, or directly you can see that they are image patches means for you that is information only. Okay, information in terms of the pixels. Okay, that you must remember, x and y both pixels across the entire width of the image. Okay, width and length of the image. Okay, in a way that's dependent of overall signal energy. Key difference is whether or not you first subtract off the signals mean. Okay. For normalization, what we generally do, some noise would be there, some interference would be there. We try to eliminate that by subtracting off with the mean. Okay. That we try to do. Okay. Normalized cross correlation NCC. Okay. NCC is f dot g over double mod f and mod of g. Okay, already I told you how this is particular thing is computed, but in case of your ZNCC, it would be somewhat different. It would be summation fi minus f bar gi minus g bar. Okay, those particular terms in product divided by under root of fi minus f bar whole square under root of gi minus g bar whole square. Okay, so ZNCC particular term would be there. Okay, mean subtraction, zero mean. Okay, it is invariant to both scaling and addition of constant offset. Okay, that components or that particular operations won't be affecting its individual performance. Okay, so this is regarding NCC, this is regarding ZNCC, why we are doing things that already I told you. Okay, So key differences you try to see here, subtracting mean. In case of NCC, it is not there. Then invariant to scaling, yes, both are invariant to scaling. Invariant to offsetting, no, but ZNCC is invariant to offsetting also. Then robustness to lightning, yes, it is lower, but ZNCC is higher. In case of the robustness is very high because you have to first compute the mean for entire range of the pixel. Okay, so robustness will increase there. Okay, then common is image matching. Yes. Okay. NCC is common, but ZNCC is preferable if you want to uh, eliminate the particular notion of light. Okay. So if you want to eliminate that, then only ZNCC would be of much use to you. Okay. Yes. Then when to use which? You have to use NCC when you care much about the contrast. Okay. Normalized similarity. Okay, ZNCC you have to use when you need to be insensitive both to contrast and brightness. Okay. So using both of these particular concepts is in your hand as a design engineer. You have to design the pipelines for image processing in those particular domains, in those particular cases. You have to switch, you have to use things based on their use cases. Okay. Yes, in summary, formula have been given here for NCC, for ZNCC. Okay. The extra zero mean step in ZNCC makes us robust to additive biases, okay, which is why it is popular in case of your stereo matching, in case of your template matching, in case of your optical flow under varying illumination conditions. Okay. So next question, please take a pen and paper. Please at least try to jot down what is the question, what are the different things. This particular concept I dealt it in practical form and manner. Also I try to show you some of the concepts. Okay, yes. Okay, one very important thing is there, sir. ZNCC, how could we change the lightning as preferable? Can't we change without light? Okay, see, I will try to explain you once again. Okay, in case of your ZNCC, the thing which is happening, the basic denomination which is happening is you are subtracting each and every Fi and Gi from its mean. But in case of your NCC, okay, the direct terms are being multiplied. What I mean to say is that Z and CC is invariant to change in lightning conditions. Because if you will see a particular image, if the lightning condition will change, then the pixel intensity values of each and every pixel at a given image will change by scale up or scale down by a constant number. That is what I want to say. So, in whatever amount you will be changing the lightning conditions, since I am subtracting it from the bar, from the mean value of the pixel, so it will be invariant to the change in lightning conditions. What I am particularly about Z and CC. Okay, you don't have to change the lightning condition. I was just explaining you that Z and CC in itself is inherent or in it doesn't get affected by change in lightning condition. That is what I wanted to say. Okay, if you are in such a state that across the entire domain of the data set, okay, if you see a particular data set and in that particular data set lightning conditions are changing very rapidly, then in those particular cases you can use ZNCC because it is inherent and it does not get affected by ZNCC since we are subtracting each and every pixel value from its mean value. Okay, but in case of your NCC, it would be affected by the change in lightning conditions because directly we are multiplying the pixel values f into g summation divided by summation fi square summation gi square. Okay, is it clear now? Or still, if any doubt is there, then please ask me. Okay, 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 very good. If anybody is having any doubt at any point of time, please ask me. Okay, very few students have joined. Okay, that is why there is no hesitation. Feel free to ask. Okay, even if the strength is large, feel free to ask. Okay, I'll be happy to clear your doubts and I'll be able to you will be able to get the right concepts. Okay, that is my intention. Yeah. Now coming to question number 2, please jot it down. Okay, at least jot it down, then you can see the solution yourself. Okay, and if such a type of question is asked in the examination, then you can very easily answer it. Let D1, okay, particular value has been given, which is 10, and D2, which is the value has been given as 8. Okay, be the distances to the nearest and next nearest neighbors from a query feature, respectively, for a threshold limit of 0.6. You have to choose the correct option. First option is nearest neighbor distance ratio d1 by d2 accepts nearest neighbor as a match. Then second option is nearest neighbor distance ratio d1 by d2 rejects nearest neighbor as a match, or both A and B, or D, none of the above. Okay. These are the four different points. Okay. You just have to see them. This particular question is related to Lewis ratio test that we already covered in previous week. Okay. In previous week also, week number 6, as well as in week number 5, I have covered this concept in great detail along with the practical applications also. Okay. The recording links as well as the PDF links are there in this particular Google Sheet. Okay. Feel free to use it. Okay. For your own good. Okay. See here, the correct option would be option number B. Okay. Nearest neighbor distance ratio d1 by d2 exceeds the distance threshold 0.6. Okay. Three things were provided to you. D1 was provided to you, D2 was provided to you, as well as a threshold limit of 0.6 was provided to you. And you were asked to correctly solve this particular question along with the options. Okay. See here, there is a particular ratio test which is the Lewis ratio test. That is particular terminology, that particular concept we will try to use here. Okay. D1 is the distance to the closest best match, and D2 is the distance to the second closest match. Then you have to compute the ratio. Ratio R is D1 by D2. Okay. Match is only accepted in those particular cases if your R is less than T, where T is the chosen threshold. In your case, it is 0.6 as given in the question. So you try to compute the ratio. Okay. D1 is 10, D2 is 8, 10 upon 8 is 1.25. Okay. So 1.25 is far, far greater than 0.6. Okay. So in general, I'll be very confident to say that nearest neighbor ratio distance D1 by D2. Okay. It rejects neighbor as a match. Okay. If it has been less than the given threshold value, then I would have said yes, the nearest neighbor distance accepts nearest neighbor as a match. Okay. So this particular concept is very, very useful in computer science. Okay. This particular concept is known as Lewis ratio test. Okay. Yeah. So in case of your in in many feature matching pipelines, that is SIFT, surf, or both, all three of them I have covered in great detail. Okay, I showed you the codes also. Okay, and we try to see the practically also these particular concepts. Okay, feature matching pipelines, shift, surf, or a single query descriptor often fires on multiple database descriptors. Okay, to decide whether its best match is truly unambiguous. Okay, so the scientist Lowy. Okay, he introduced the nearest neighbor distance ratio and the NNDR test. Okay, so a query feature queue in one image is compared against all features in the other image. Okay, you have to compute the distances, Euclidean distance, Manhattan distance, or whichever you would like to calculate, you can calculate from queue to each database descriptor. Okay, where D1 is the distance from queue to its closest match, and D2 is the distance from queue to its second closest match. Okay, so D1 and D2 you try to compute. Then, if the two nearest distances D1 and D2 are very similar, okay, that means that there are at least two almost equally good matches, making the correspondence um, correspondence ambiguous. Okay. Ratio test is R equal to D1 by D2. You have to use a threshold T. Okay, T approximately here has been chosen as 0.6. You have to accept the match as if R is less than T. Okay, meaning the best match is significantly better than the runner. Okay, reject that particular match if R is greater than or equal to T. Okay, so both of the things are there. If R is less than T, okay, then you have to accept the match. If R is greater than equal to T, then you have to reject the match. Okay, so it works for your disambiguation, it works for your illumination, viewpoint changes, it works for your adaptive per feature. Okay, and numerical example already we have seen why we have rejected according to Lowe's ratio test criterion. Okay, so these particular things are there. Okay, next the KL distance you have to find between A and B with the probability distribution zero point 0.2, zero point 0.4, 0.15, zero point 0.1, 0.05, and zero point 0.3, 0.35, 0.05, zero point 0.2, and 0.15. This particular concept is very useful. KL distance, okay, very important for you to understand how to calculate. I'll just try to show you. Okay, please at least jot down the points. Okay, A point, what is the probability distribution? B point, what is the probability distribution? That I'll try to show you step by step how you can calculate the KL distance between A and B. Okay, now we'll try to just see what is the KL distance. Okay, here if you will try to see a particular distribution, okay, the Lablet divergence is the full form KL divergence. Okay, sir, we need to find both A and B probabilities. A and B probabilities have been already given to you. Okay, A has been given to you, B has been given to you. You just have to apply this particular formula, which is summation I equal to 1 to 5. Okay, AI log of natural log of AI over BI. Okay, where AI will be the coordinate, the probability distribution of the first point. B is the probability distribution of the second point. Okay, so AI and BIs are already given. You just have to compute the natural log of AI and AI over BI. Okay, so that you try to compute in the third column, and then you try to multiply with the first point. Okay, AI natural log of AI over BI. Okay, that you try to compute. Okay, and then at the end you sum all the values. Okay, that particular summation will give you the Kullback Leibler divergence or KL distance. Okay, total divergence would be nothing but the sum of this particular column, that is 0.01287. Yes, this will match with option A, I think. Okay, A and B probability distribution has been already given in the question. You just have to plug in into the formula. DKL equal to summation I equal to 1 to n AI natural log AI over BI, where AI is the are the coordinates of the first point, and natural log AI over BI you have to compute, where BI are the probability distribution of the second point. Okay, so that you try to compute. After computing, you sum all the values and you will be getting exactly this particular value, 0.01287, 0.01287, that you will get. Okay, that you will get, and that is the exact value, okay, which we you were looking for. Okay, so yes, any doubts in this particular question? Can we move forward? Is it clear? Direct implication of a formula is there. If it is clear, then please say it. So table is mandatory in this question. Yes, table is not mandatory in this question, but it would be helpful for you to compute, because if you will make the table and then you try to calculate the values term by term, then your chances of committing calculation mistake in the examination would be very, very minimal. Okay, that is why it is my own suggestion. Please use the table for calculation, because see here, the options which you are seeing here, they are very close. Okay, so your chances of committing mistake are very, very high. Okay, and it is in the pressure of the examination only sometimes we pick the wrong options. Okay, if you would be getting a value around 0.1, you would be immediately picking up the option number B. You won't be even checking. Okay, so that is why it is a sincere advice. Okay, use the table for the calculation. Okay, thereby you will not get uh, any doubt or any mismatch in the options. Okay, clear? Can we move forward? If it is clear, please say we can move forward. Otherwise, please ask me if any doubt is there. Clear? Answer log table will be provided. Yes. Either log table, natural log table would be provided to you, or you would be allowed to carry your scientific calculator, or third possibility is there that you would be given a virtual calculator. Okay. Three possibilities are there. Without natural log table, nobody can calculate this particular question. Okay. So there are three possibilities. Either you would be given log table, okay, as well as sine table, tan table, cosine table, all the tables you would be given. First possibility. Second possibility is there that you would be allowed to carry your scientific calculator. Third possibility is there you would be getting a virtual calculator. Okay, like in the gate examination, there is a particular virtual calculator that you would be getting. Okay, so whichever possibility is there, that would be written in the admit card. Okay. So feel free to go through it in the instruction itself. It would be given whether you are required to carry your scientific calculator, or you would be given one, or you would be given able. Okay. Okay. If it is clear, then let us move forward. Question number 4 is RANSAC is best suited to find optimal line parameters when points belonging to a line are given. Okay. Please try to say whether it is true, whether it is false. or you don't have any opinion, then still say, okay. There is no hard and fast rule that you would be correct in the first attempt, but at least try to say whether this particular statement is true or false. Okay, you are saying true, it is not true, it is false. Okay. Why it is false? RANSAC. Okay, RANSAC is a robust randomized method designed to handle datasets with a significant fraction of outliers. Okay, it repeatedly samples minimal subsets, finds fits a model, then selects the model with the most inliners or the points which are matching uh, uh, with the correct correlation line. Okay, so it will sacrifice the optimality for robustness. Yes, this is true. When all points truly lie on a line, no outliers are there, then ordinary least square fitting yields the analytically optimal line. Okay, minimum squared error in one deterministic pass. Rensec drawbacks in the no outlier case are randomness of optimality. Okay, in short, if you know the advance that every point belongs to the line, classical least squares is both faster, yields a true optimal fit. Rensec excels only when you need to reject the outliers. Okay, this is the thing. Rensec means random sample consensus. Okay, it's an iterative, robust estimation algorithm introduced by Fisher and Bowles. Okay, for fitting models to data that may contain a high proportion of outliers. Outliers are the points which don't follow the linear regression or the optimal regression pattern which we are trying to fit. Okay, those particular points are the outliers. For example, if you are given simple x and y points, okay, distribution you have been given, and you are trying to fit a linear regression line, then these all points which are not fitting, okay, they will be termed as outliers. Okay, outliers. Okay, there would be nothing but the outliers. Okay, so this is regarding your iterative robust estimation algorithm introduced by Fisher and Balls, okay, for fitting data that may contain higher number of outliers. Okay, instead of trying to fit all data at once, RANSAC will repeatedly sample a minimal subset of the data. It will try to fit a model. It will measure how many of the total data points agree within this model and keep the model that has the largest consensus set. Okay, that is the thing. It's a step-by-step algorithm. Input would be data points xi, yi. Error threshold would be summation. Error threshold would be epsilon. Okay, desired confidence would be p, and the minimal sample size is s. The number of iterations is n equal to ln natural log 1 minus p over ln 1 minus w raised to power s. W is the inliner ratio estimate. If you are guessing that out of the points which you have been given, 50% of the points would be falling in, within the range of your linear regression or your regression fit line, then you can guess W is zero point 0.5. Okay, so number of iterations you can compute using this particular formula. Then you have to repeat for k equal to 1 to n. Okay, randomly pick any s then fit the line, then count the number of inliners, then record the size of the consensus set, okay, and the model parameters if it's largest so far, okay. Then refinement, yes, you can refit a line, okay, in order to improve the accuracy, you can still refit a line. And output would be a model with the highest inliner count. Okay, this is the thing regarding your RenSec algorithm and step-by-step evaluation. Why RenSec is a particular algorithm which would be excelling with the outliers? Because of outlier rejection. By counting inliners rather than minimizing squared error overall points, RenSec will completely ignore points that don't fit. Even if 50% of your data are gross outliers, there is still a reasonable chance that in one of the random samples you will only pick the inliners. Okay. Flexibility is there because a lot of model parameters are there. Okay. There are various limitations also for your RenSec. Okay. First of all, the major limitation which you will be facing is randomness and computation. Okay. You have to repeatedly run the particular algorithm with a many number of iterations. Okay, each iteration fits a model, checks all the points, potentially expensive. Okay, final result can vary run to run unless you fix a random seed. Okay, not optimal in case of your noise free case. Okay, then threshold sensitivity is there. Okay, yes, the dependent parameter is there. Then guaranteed consensus versus global error. Yes, RenSec optimizes the inliner count, but not your mean squared error. In a pure inliner set, maximizing count is trivial. So the best RenSec sample may actually be suboptimal. Okay, in terms of fitting quality. Yes, this is a particular limitation of the algorithm. Okay. Then when to use what? Okay, if there are no significant outliers, okay, then you for your faster or your optimal convergence you can use for least square regression. Okay, OLS, ordinary least square regression, you can use for your moderate outliers. You can use M based estimators. Okay, Uber loss is there or any other estimator is there that you can use. If your fraction of outliers is large, then you can use RenSec. Okay, if your outliers plus are there, okay, as well as there is noise, okay, then you have to modify your pipeline and you have to include a refinement procedure or refinement algorithm along with your RenSec. Okay, so these three possibilities are there. Okay, you can try to use according to you can try to use those according to your cases. Okay, whichever data set you are encountering with, you have to see accordingly. Okay, you have to use the algorithm accordingly. Okay, so see that particular thing. Okay, you are encountering which type of data set. Okay, then you have to use the algorithm accordingly. Okay, moving forward, which of the following methods is best suited for line fitting with outliers? Please provide your opinions in the chat box, whether it is least square, whether it is RenSec, whether it is half transform, whether it is your KL divergence or the Kullback-Leibler divergence. What do you suggest? Okay. Best suited, which of the algorithm is best suited for your uh, line fitting with outliers? Okay. Yes, we have just encountered with an option RenSec. Good. The rest of the students, please provide your opinions. There is no hard and fast rule that you need to be correct. There is no penalty on being correct at the very first attempt, but at least try. Okay, this is my intention. Okay, yes, the correct option would be 110% RenSec only because I already told you so much information about RenSec. Okay, It would be ransack only. That option would be correct. Okay. Why? Because least squares assumes all points are inliners and minimizes the squared error, so it's easily skewed by even a few outliers. Then ransack repeatedly samples minimal subsets. It fits a line, picks up the model with most inliners. Okay, making it highly robust when outliers are present. Okay, and half transform can detect lines in noisy data, but typically requires discretization in parameter subspace. It can struggle with many spurious points or parameter tuning. Okay, this particular half transform, this is a very important concept in computer vision. And in present session, I have prepared two particular Google Colab notebooks. I'll try to demonstrate you what is this half transform. Okay, how it actually works. Okay, as well as how you can apply this particular concept in your own research. Okay, then Linear divergence, it measures difference between probability distributions. It is not used for geometric line fitting. We already have solved a particular question there, where you have seen that a particular probability distribution of two different points has been already provided to you, and you have calculated KL divergence there. Okay, so that is the thing. Then comes your next question. Low training error necessarily indicates overfitting. What do you say? Is it true or is it false? Okay, false, false. Okay, good, very good. Yes, indeed, this statement is false. Low training error, but large test error indicates overfitting. Okay, low training error will not necessarily indicate overfitting. Okay, you cannot say anything unless until you have tested the model. Okay, so from the training data itself, you won't be able to say much. Okay, that is the thing here. Okay. So it is false. Why false? Because training error measures how well a model fits the data it was trained on, and overfitting occurs when the model fits the training data too well, capturing noise or spurious patterns, okay, so that it performs poorly on new unseen data. Okay, having low training error is a necessarily condition for overfitting. Okay, so you can't overfit if you don't fit the training data. It won't be sufficient on its own. Model can achieve low training error and can also generalize well to test data. This is the goal of the good model. Okay. So low training error, it means the model's predictions match the training labels. It can result from having a sufficiently expressive model, ample amount of data, and proper regularization is there. Okay. Overfitting, it can be detected only by comparing training versus the validation or the test error. Okay, if training error is far less than the test error, that the gap would be indicating your overfitting. Okay, and in my personal experience, practically, I have seen that whenever we are beginners, we try to fit a particular model, whether it is a machine learning model, whether it is a computer vision model, whether it is a deep learning model. The major point in major cases we encounter this particular overfitting. If you would be seeing your training data and you would be comparing the model performance along with it, it would be 100%. Okay, in some of the cases I even have seen that the fitting reaches with a coefficient of determination r square is 0.9999. Okay, but those particular models fail very badly when it comes to test data set, unseen data set. Okay. In those particular cases, the model fails terribly or miserably. Okay, that is the case. So yes, overfitting can be detected only by comparing training versus the validation test error. Okay, if training error is very less than the test error, then that gap indicates overfitting cases. Okay, so no one can guarantee from training error alone. Okay, no low training error plus low test error. Yes, it's a generalizable model. It's a well-fitted model. If it is a low training error plus high test error, then it is a overfitting model. Okay, it has to be retrained. Okay, that is the thing. Yes, there are particular scenarios. Okay, as a design engineer. Okay, if you are working as a design engineer. Okay, if you must understand these particular illustration, these two particular scenarios. Okay, that I have demonstrated here. If it is a small linear model fitted on no if it is a small linear model on linear data and your training error is low, your test error is low, it's a good fit. Okay, always please try to understand your training error would be somewhat lesser, your test error would be somewhat more, but no need to worry about that. Okay, but both should be low. What do you mean by low? It should be within 10%. Okay, errors within 10%. And those particular cases in those particular figures would be given as a target to you. Okay, you have to reduce the error within this particular range limit. You have to reduce the error within that particular range limit that would be given to you. Okay, so you need not to worry much about it. Then second particular case was huge neural network on limited data. Okay, huge neural network is there. Hugeness of the neural network doesn't mean that it would be big, it would be having multiple layers. That is the thing. Huge neural network on limited data, the training error is low, the test error is high. Okay, it means overfitting. Okay, very underpowered model means lower number of layers, whether they are hidden layers, whether they are input layers would be constant, output layer would be constant, mainly dealing with the hidden layers. Okay, so training error, if it is high, test error also it is high, it is underfitting. Okay, case of underfitting, you need to increase the number of epochs, you need to increase the number of iterations, then only it would be a good fit. Okay, that is the thing. Only the second scenario is true overfitting. Even though all three may exhibit low training error in the first two cases, the second shows large gap to validation error. Okay. Question number 7 is consider 2 points A and B in image space. You have to compute two lines corresponding to them in parameter space. Okay. A has been given to you. Okay. And you have to B has been given to you in image space. You have to compute the two lines. Okay. Please try to solve using your elemental mathematics only, class 12 mathematics only. Please try to solve this particular question. I'll give you solid 5 minutes. Okay. Then I'll be telling you what is the correct option. Okay, and what is the particular approach. Very simple question based on elemental mathematics. You already have seen it in your class 12. Okay. Simple line equation you try to use. Okay, and try to fit a line. That is the thing. Yes, very good. Option C is equal to minus m plus 3 and is equal to minus m minus 3m plus 5. Okay. Then y equal to mx plus c. By using this formula, we can solve sir is equal to minus m plus 3 is equal to minus 3m plus 5 is the correct answer. No, I think is equal to minus mx plus y. Okay. So I've read whatever you have written. Very, very interesting. Okay. Indeed, you both were correct. Don't get confused. Okay. It's a very simple question. Okay. And y equal to mx plus c and is equal to um, minus mx plus y. These are the both the denominations they are being used. Okay. Nothing much complicated is here. Okay. So point A is 1 comma 3. Okay. Point B is 3 comma 5. Okay. So y equal to mx plus c is equal to y minus mx. Okay. So c equal to y means 3. Okay. Points here have been given. Okay. 1 comma 3 and 3 comma 5. Okay. I'll note it them down here. 1 comma 3 and 3 comma 5. Those were the points. So from point 1 comma 3, okay, c equal to y minus mx. Okay, that only I'll use. Y is 3. Okay, 3 minus mx. M is 1. X is 1. So m into 1, 3 minus m, that is c equal to minus m plus 3. This is the first line. Then b equal to 3 comma 5. Okay, c equal to y minus mx. Okay, y was 5 here and minus m into 3. Okay, so 3m. So c will be minus 3m plus 5. Okay, so c equal to minus m plus 3 and c equal to minus 3m plus 5. Okay, those are the two particular lines. Okay, just 1 second, guys. There is some issue with the network or anything. Okay. Yeah, everything is clear. Tab just got some update. Okay, no problem. Yeah. So those two are the points. Okay. Yes, c equal to minus mx plus y, that only denomination we are using. Okay, no problem is there. C equal to minus mx plus y, that only denomination we are using, and using that particular denomination only we are yielding particular values. Okay, c equal to 3 minus m into 1 minus m plus 3, c equal to 5, c equal to 5 minus 3m, that is minus 3m plus 5. Okay, so those two particular denominations only we are trying to use, and we are comparing the results here. That is the thing. Okay, corresponding option would be option number C only. Okay, don't get confused in the examination. And coming to the next question, compute the cosine similarity between two particular points A and B, 3 comma 2 comma 8 comma 2 comma 5 and 4 comma 2 comma 8 comma 9 comma 4. This is particularly very important. Okay, cosine similarity between these two points, 32825 and 42894. Okay. Okay. So cosine similarity or the cos similarity we have just computed in the first question. We have seen the formula vector A dot V over modulus of vector A, modulus of vector B, or the length of vector A, length of vector B. F has been given as 32825. G has been given as 42894. Then you try to compute cos theta. Cos theta is the angle or the cosine similarity between two particular vectors. It would be F dot G over modulus of F, modulus of G. Okay, where modulus F is nothing but the length of the particular vector. Okay, F dot G, you try to compute the element wise dot product. Okay, 3 into 4 plus your 2 into 2 plus 8 into 8 plus 2 into 9 plus 5 into 4. These are the elemental dot products that we'll just try to calculate, and that would be coming around 118. Okay, that would be coming exactly as 118. Okay, then you try to compute the norm. Okay, norm is nothing but the under root square sum of squares of all the particular elements. Okay, that is 3 square, 2 square, 8 square, 2 square, 5 square. Okay, so that would come around, and under root, if you will take, it is under root 106, that is 10.2956. Okay, and modulus of G, that would you try to compute 4 square, 2 square, 8 square, 9 square, 4 square, that is 16 plus 4 plus 64 plus 81 plus 16, that is under root 181, that is 13.4536. Okay, cosine similarity is nothing but cos theta, that is F dot G, that is 118 divided by this modulus F, modulus G, that is 10.2956 multiplied by 13.4536. Okay, 0.8519. And this is the cosine similarity rounded off to 3 decimal places, that is 0.851. Okay, so moving forward, question number 9, choose the correct options. Half transform requires appropriate resolution of discretization of the grid in parameter space. And if grids are too coarse, too many different points in image some space mapped to single bucket, or if grids are too fine, some points may not exactly be collinear, voting different buckets, or half transform does not require any discretization of grid in parameter space. Okay, so please try to answer. Okay, try to at least guess which option would be correct. Okay, all these statements are regarding half transform only. Okay, Okay, A, B, C are correct and D is false. Okay, let us see. Yes, A, B, and C are correct. D is false. Okay. First statement was true. The half transform casts each image space point into a curve in a discrete parameter space. Okay. You must have to choose a finite resolution for that grid. So appropriate discretization bit is essential. Otherwise, the balance and accuracy would be lost. Statement A is true. Statement B is if your parameter space bins are too coarse, larger is del rho or del theta. Okay, then many distinct lines in the image, that is many different points in image space, will all vote into same space bin. Okay, same big bin. It will lead to poor localization and merging of nearby lines. Yes, it is true. Then C statement is also true. Conversely, if your bins are too fine, that is, it is delta rho is smaller, delta theta is also smaller, then points that should lie on the same line may each vote into slightly different neighboring bins. Okay, spreading their votes, making the line peak less pronounced. Okay. So statement A, B, and C are true. D is false. Okay. You do need to discretize the parameter space into bins. No exact accumulator is there. Okay. Without discretization into the classical half method. Okay. So yes, A statement is true. B statement is true. C statement is true. It requires discretization. Hence, D statement is not true. Okay. So this was regarding. Sir, how C is correct? Could you please explain? Yes, C is correct. How it is correct? I'll just try to explain. See, statement number C is if grades are too fine, some points may not be exactly collinear voting different buckets. What the statement is trying to say, in half transform, we try to create the grades. I'll just try to show you after the next question only. I'll try to demonstrate the steps using the Google Colab notebook. There you will see that we try to create some of the grids, okay, prior to applying the half transform, okay. But the statement is saying if you are creating two fine grids, okay, some points may not be exactly collinear voting different buckets. Means what the thing it is trying to say that if you the mesh size if you will try to create it is very fine, okay, if grids are too fine, okay, means the abnormality is not there, okay. So within the within two particular grids, okay, within two particular grids or between the grids, the exactly collinearity wouldn't be there because the fineness is too high, okay. If the fineness is too high, then the algorithm will compute each grid, okay, separately. The features would be computed separately, okay. There wouldn't be much overlap between the grids, okay. So thereby the results, the features which we want to extract, they won't be fetched, okay. So this statement is uh, statement number C is trying to say that particular information. Okay, I hope it is clear. If it is not clear, please bear with me. Okay, I'll try to demonstrate this particular concept using the Colab notebook that I have already prepared for you. Okay, thereby you will see that we first try to create meshes. Okay, after meshes, we try to overlap them, and after overlapping only, we come to the conclusion that the which feature is essential for us and what is the feature similarity between different bits. Okay, on the basis of that only we try to take the decision. Okay, that is the thing. Okay, we shall move forward. Okay, in classic half transform, each image point x comma y, it votes for all lines that could pass through it, mapping into curves in a chosen parameter space. Okay, most often it is rho theta or it is mc. Okay, both the denominations y equal to mx plus c or y equal to rho x plus theta. Okay, these type of denominations we can use. Okay, to implement this in practice, you need an accumulator array. Okay, you must require an accumulator array, discrete grid of bins over the parameter space. That choice of how fine or how coarse to make those bins has a direct impact on both detection accuracy and the robustness. Why discretize at all? Because the true parameter space, that is rho or theta, is continuous and infinite. Discrete accumulator will allow you to store and tally votes in finite memory. Without discretization, you cannot implement the algorithm on a digital computer. Okay. The coarse versus fine bins, the trade-off is there. Coarse means fewer bins. Okay. Means less memory, faster convergence. Votes cluster means strong peak. Cons is low angular or radial precision. Nearby but distinct lines merge into one bin. Okay. Fine means high precision in rho and theta estimates. More bins means higher memory and slower convergence. And votes from truly collier points may spread across adjacent bins. Okay. These all the things are there, technical things are there. We will try to practically see those. Okay, how those particular concepts are dealt. Okay. Then yes, if bins had two cores, merging of lines would be there. There would be localization error. Okay. If bins had too fine, there would be vote scattering, increased cost would be there, and the grid overlap, which is there for calculating the feature importance, it won't be there. Okay. So these things are there. That is why you have to choose the number of bins very carefully within that particular algorithm. That is an attribute. Practically, what are the different strategies which are available? Okay, set del theta so that maximum angular error induced by pixel quantization is smaller than half of the bin. And del rho you can relate for it to image resolution. You can take it accordingly. Okay. In Python, for both of these inbuilt functions are there, but how they are just doing that, what is the background or what is the backend that you can see, and then you yourself can create a function which can decide your del theta and del rho. Okay. Your multi-scale or hierarchical voting. Okay, first vote in a coarse grid to find approximate line parameters, then refine around with peaks with finer grid. Okay. Then Gaussian smoothing is there within the accumulator, spread each vote into small neighborhood rather than a hard bin, reducing the sensitivity to exact quantization. Okay, this particular facility is also there. Then adaptive binning is also there. Okay, different strategies are available. Okay, whichever you like to use for your particular use case, you can go ahead with it. Okay. You must choose a finite grid resolution for parameter space. Bins are too coarse. Different true lines merge into one accumulator bin. If bins are too fine, votes from single true line scatter across multiple tiny bins, weakening the peak. Okay. Balancing the bill is very, very crucial. Next is using the method of least squares. You have to find the equation of the form y equal to ax plus v, ax plus b that fits the data, and xy coordinates have been given to you. Okay, please try to solve. I know there would be a single confusion that I'll try to clarify, but let you try first. Okay, for 2-3 minutes, then I'll try to show you. Okay, yeah. Okay, if you will try to see, okay, y equal to ax plus b, and you have to fetch the least square, and points have been given to you, and number of points is 5. Okay, so first of all, you have to set summation xi, you have to calculate summation yi, then you have to calculate summation xi square, then you have to calculate summation xi yi. Okay, then you have to use this particular equation. You have to calculate a and b. A is n summation xi yi minus summation xi y summation yi over n summation xi square minus summation xi whole square. Okay. So using that particular formula, when you will be calculating A, so similarly you have to calculate formula for B, which is summation yi divide minus A summation xi divided by n. Then you would be getting B as 2, and your best fit line would be y equal to ax plus b. Okay, A is 3 and b is 2, so y would be 3x plus 2. So that particular line would be there, and that is in the option number C. Okay, that is the case. When you have the set of points xi comma yi, and you have to fit the straight line y equal to ax plus b, that best fits them, then the most common criterion is least square. Okay, and the formula is yi minus a xi plus b whole square, and a and b formula has been there. Okay, why least square is there? Because for a given line y equal to ax plus b, each point has a residual ri yi minus ax plus b, and if you will be squaring these particular residuals, okay, it will penalize the large deviations more heavily and ensure that all the terms are positive. Then minimizing summation rs square yields the a line that in global sense passes through as close as possible to all the points. Okay. Then you set up the normal equations, del E over del A equal to 0, del E over del B equal to 0, and you have to compute this particular E expression yi minus a xi plus b minus b whole square. Okay, and if you differentiate, you will get this particular terms. Okay, then differentiate E with respect to b and equated with 0. Then, if you will try to simplify, you will get summation xi yi is a summation xi square plus b summation xi summation yi equal to a summation xi plus bn. Now you try to solve for a and b, it would be a simple uh, linear system. Okay, and you would get a as n summation xi yi minus summation xi summation yi over n summation xi whole square minus summation xi whole square, and b is summation yi minus a summation xi divided by n. Okay, these closed form formulas will give the slope a and intercept b in one go. Okay, this is the thing. Then what is the geometric interpretation? Slope A is the covariance between x and y divided by the variance of x, and intercept B shifts the line so that it passes through the center of mass of the data, that is x bar and y bar. It's the best fit because among all the lines, okay, this one will minimize the average of squared vertical distances from points to the line, and it's all maximum likelihood exhibitor estimator, if you will assume that all the residuals Ri will have an independent Gaussian noise. Okay, when you don't have to use when errors are primarily in y measurement, then you don't have to use, you have to have the errors in both of the measurements. Okay, be cautious. If both x and y are having noise, then and along with that, if outliers are present, then use the concept of ransack. Okay, that is up for these 10 questions I wanted to discuss in the present session. Okay, so this is over. Okay, if any doubt is there, feel free to ask me. Okay, I'll just unshare and then I'll try to share another screen. Okay, just 1 second. Okay. Yes. Just 1 second. Share my PC screen. Okay. Thereby you can see concept of the half transform along with the requisite concepts. Okay. Just 1 second. Yes. Share my screen. Share. Okay. So let us begin. Okay. See, already I have told in my previous sessions. Okay. What happened? Why is it? Yes, yes. I think my screen is shared. Okay. Yes. Yeah. So try to see here a particular demonstration is there regarding half transform. Okay. It's a popular feature extraction technique which is used in image analysis, computer vision, as well as digital image processing, particularly useful for detecting some simple geometric shapes such as lines, such as circles. Okay. Standard, there are three types of half transforms. Standard half transform used for line detection in binary edge detected images. It is another type is probabilistic half transform, which is the optimized version that uses random sampling for efficiency. Another one is circular half transform used for detecting circular shapes. Okay. For the practical steps, load an image, convert it to grayscale, apply canny edge detection, then apply half transform, then display the results. Okay. So first of all, I'll reconnect this particular notebook. Okay. Yes, connection has been made. Then I using the run all command, I'll try to run all the cells. Okay. In this particular notebook, what I am trying to do is loading an image, then converting it to grayscale. Why I am converting it to grayscale? For faster execution. Okay. R, G, and B would be having three distinct set of pixels. I'll be reducing it to only one set. Okay. That is uh, black and white values from pixel values from 0 to 255. Okay. Then you apply half transform, then you display the results. Okay, see in first cell, I have tried to install this particular library scikit image. Okay, then I have tried to import CV2, then NumPy, then matplotlib, then skimage. Then I use utility function to display images. Then I loaded the Sudoku. Okay, this is a particular image. Okay, from this particular URL. It's an open source URL. Then after that, I try to convert that particular three channel image, okay, into single channel, which is grayscale image, okay. Then I try to show both the images. This one is the original image, okay. Only the original images only I have tried to display it, okay. Both of the original images, two images I have taken as the reference, okay. Then I have to perform this particular line detection using the half transform. First of all, we will use the canny edge detector. Then we'll apply the half transform. Okay, converting again to grayscale. Okay. Then for edge detector, a particular function, canny edge detector function is there that directly I have applied. Then I have used show image along with that. I have provided the parameters, canny edges. Okay, and I have given the lines as gray. Then I have applied the half transform. Okay. Then draw lines on a copy of the image. Okay. That I have done. These particular lines I have tried to draw, and then I have tried to show what are the detected lines. Okay. canny edges are like this, okay, and the lines which I have detected in this particular image have been shown here in red. Some mistakes are there, okay. This is the region where some mistakes are there, okay, that would be present, as well as here you can see overlap is there, okay. So those will be present, okay. These are the particular errors that are further, if you want to refine, that is done using Gaussian smoothing. Okay, Gaussian smoothing as well as denoising filters are there that you can apply, further enhance the accuracy, but the major part is done here. Okay, then circular detection using the half transform. You will use the circular half transform here on the to detect the circles in the another image. Okay, same steps are there. First of all, you have to convert into the grayscale image, convert it into three channel image. Okay, then you have to pre-process, then you have to apply the circle transform, and this is the function. Okay, then you have to provide an for loop. Okay, inside that the detected circles would be shown. Okay, so see here a lot of circles are shown, some of it them are correct, some of them are incorrect, as well as a lot of overlap is there, but this is the basic insight. Okay, as well as some conclusion is there. Standard half transform, it detects infinite lines. Probabilistic half transform, it detects line segments efficiently. The circular half transform, it detects the circles. Okay, now another example, I have detected lanes. Okay, lanes in a particular image using the standard half transform. In this demo, I have used the half line transform for autonomous driving as well as your ADAS. This is the most advanced driver assistance system, okay, that is there, as well as in your autonomous driving. These all the concepts are used. You have to load a road image, then you have to convert it into grayscale, then you have to apply the Gaussian blur to reduce the noise, denoising the image. Then you will use the canny edge detector, okay, to find the edges. Then you have to mask the region of interest, then apply the probabilistic half line transform and draw the detected lines on the original image. Okay, so installing dependencies, then loading image from URL, then displaying the image. Okay, these are the same steps. Okay, original road image that I have just downloaded from GitHub. Okay, open source image is there, URL has been given to you. These are all the notebooks I'll provide you as a link. Okay, in the same folder in which you will find the notes. Okay, try to download them, run them, and use them for your research projects also. Okay, then you pre-process the information. You first of all apply the grayscale conversion, Gaussian blur, then canny edge detection. All these steps are there. Okay, after canny edge detection, this particular one is the output. Then you mask the region of interest. Okay, where the lanes are expected. That particular masking is the only attribute which is somewhat tricky. Okay, create a mask for region of interest in which this particular case, the mask shape which I have used is of trapezoidal shape. Okay, so region of interest, if you will try to apply the trapezoidal shaped mask within entire image, then you will be able to segregate the region of interest, and after applying the probabilistic half transform, you would be able to detect the lanes like I have detected. Okay, so conclusion is this: you have used edge detection plus region of interest segmentation plus half transform in order to detect the lanes, and you have simplified the lane detection pipeline using self-driving cars. And particular extension is there. You can use it for road images. You can just try to play with the threshold minimum length and the maximum line gap, and extend the video lane detection by processing each frame. These particular steps you can try to follow. Okay, so this was my first notebook, okay, that which I wanted to show. Then the second notebook, okay, that also I'll try to show you here. Okay, this is another notebook. This is a much detailed notebook. First of all, how to create it, I already told you. Open collab. After opening collab, okay, You just have to create, click here, new notebook, then you can create a new notebook. Otherwise, you go to upload whatever file I'll be sharing with you. Then you have to tell the computer using, tell this particular interface what is the path of that particular file. Okay. Then it would be automatically loaded and you can run like I am running. Okay. So here I'll just try to reconnect. Okay. In your case, whenever a new notebook is connected and you press here run all, then automatically runtime is connected there. Okay. Then I'll use run all command. Okay. Run all the cells in the this particular notebook. Okay. Yes. What happened? Yeah. All the cells have been, I just ran them at once so that I can explain you in brief what I have done here. Okay. See here, first of all, I am importing all the necessary libraries. NumPy is NP, CV2, then Google Colab, patches, okay. CV2 I am show, then Matplotlib for plotting the graphs, then IPython, okay, for displaying markdowning, okay. Then warnings I have just ignored, okay. Then if this particular import has ran successfully, then it will show me that all the libraries have been imported successfully. So it's showing me that particular thing only. Okay. Then here I didn't uh, mm, download any of the image from any of the open source data set. Rather than that, I have created my own image. Okay. So I have created it using this particular command cv2.line. Okay. And I have created horizontal line, diagonal line, then vertical line. Okay, this is the particular pattern. And then I have displayed the test image with the lines. Okay, that I have just tried to show here. Okay, then function to demonstrate half line transform, define demonstrate half lines. Okay, half line transform demonstration, create a test image, then apply edge detection. Same steps are there. Okay, then applying half-line transform, creating copy of the original image to draw lines. And these particular steps are there. And I am searching the entire image subspace and then I am trying to draw the lines. Okay. Then the particular parameters I have just shown you. Okay. Just 1 second. I try to minimize this. Yeah. See here, original image is this one. Then after edge detection, this is the image. Then detected lines directly I have got. Okay. Why in this particular case the accuracy is much less? Because this image also I have created using the OpenCV library. Okay. I have not taken input as a raw or a natural image. That is why the accuracy is much larger here. Only all these steps, same steps, I have just tried to input. Try to do the same as I have done in the previous notebook. But why the accuracy is much higher here? The simple reason is this, because I have just taken the raw parameters and I have not taken a natural image. For a natural image or an original image, the error margin would be much higher. And in those particular cases, you have to adjust the transform parameters, which are rho, theta, and threshold. It has been given here. Rho is distance resolution of the accumulator in pixels. Theta is the angular resolution of the accumulator in radians, and threshold is the accumulator threshold parameter or minimum number of volts. Okay. Then function to demonstrate probabilistic half-line transform. Okay. Create test image, then apply edge detection, then displaying results. Same thing is there using probabilistic half-line transform. Okay. One particular difference is there, okay, in case of your probabilistic half-line transform and your half-line transform, and although the original image is same. See here, one particular mismatch is there here, as well as at the corners, a particular mismatch is there, okay, as well as it is extending in this particular direction. But when you will apply this particular one, probabilistic half-line transform, okay, then that particular error margin is reduced. Okay, see here, very sharp images, very sharp lines we have obtained. Okay, because it is probabilistic and it is more efficient version. It can detect line segments rather than infinite lines. Okay, but uh, a trade-off has to be always there. Okay, if you would be increasing the line segment, increasing the accuracy, then you have to compromise on the computational complexity sometimes. Okay, as well as faster convergence that you have to see. For practical applications, I am telling you this. Then in this particular cell, I have just applied the half circle transform. Okay, half circle transform. Okay, circle transform that I have used. Okay, so for that, I have used a particular original image. Then I have blurred that particular image. Intentionally, I have blurred. Okay, in order to eliminate the background with the foreground. Okay, then I have detected the circles. Okay, yes, I am able to detect with these circles with some amount of overlap. Okay, so transform parameters are this particular one, dp, then minimum distance, then parameter 1, parameter 2, minimum radius and maximum radius. Okay, these are the particular parameters. I've written this so that after the class is over, you just download this particular notebook, try to run in your own system and try to see whether you are able to adjust these parameters and what are the results which you are able to obtain. Okay. Now, in this particular thing and this particular cell, I have downloaded a more complex image, okay, from open source dataset. I'll just try to show you this particular image, and then I have tried to apply this particular half transform. Okay, here I have used the probabilistic half transform. Okay, so see here, original image was this one. After edge detection, it is this one, and the lines which I am getting are these one. Although the results are not that much impressive, but I have tried to apply that particular concept. Okay, the results can be more impressive only when you tune the parameters. Okay, tune the parameters according to your own data set. That is the thing. Okay, so see here, then another thing, interactive parameter exploration. Okay, this particular function I have created, interactive parameter exploration. Okay, adjusting the half transform to see how it will affect the detection accuracy. Okay, particularly I have created a sample image, simple image, then I applied the half transform. Okay, then try to see here. Okay, in this particular case in which the threshold there is minimum threshold. Okay, then try to see here, this particular one is the edge map and the half lines which I am getting are like these. Okay, number of lines which are detected is 8. Although if you will count, it is 1, 2, 3, 4, 5, 6, 7, and 8, 9, 10, 11, 12, 13. 13 number of lines are there, but it has detected 8. No problem. Then in this particular case, it was of low threshold. Okay, if I increase the threshold, okay, then what are the number of lines detected? It is still reduced to 6. Okay, then in your example 3, you increase the minimum line length. Okay, then still you would be getting number of lines detected as 8. So in this particular cell, you can adjust the different types of parameters and try to see yourself that how the lane detection or how the line detection is being affected by the different types of parameters. Okay. Then this is the summary. This is the conclusion. Okay. Half transform. It's a powerful technique for detecting shapes in images. It is working by transforming image space to parameter space and using a voting mechanism. Okay. Then OpenCV, it implements both line and circle detection, provides implementation for both line and circle detection. And parameter tuning, it is in general very, very crucial, okay, for your both line and circle detection. And uh, advantage is this particular one, robust to noise, partial occlusion conditions also, it would be able to eliminate. It can detect multiple instances of shapes. It works well with edge detection algorithms. These are the advantages. Limitations are these particular one: computationally expensive to complex shapes, requires careful parameter tuning. It is memory intensive for high resolution parameter spaces. Okay, applications include lane detection in autonomous vehicles. Okay, then industrial inspection systems, then document analysis, OCR, and medical image analysis. These are few of the applications, but your applications are not limited to those particular ones. Okay, you can extend the applications to many other applications also. Okay, then see here a particular demonstration is there: robustness to noise and occlusion. A key strength of the half transform is its ability to detect complex shapes from incomplete or noisy data. Unlike contour-based methods that might break a line into segments, okay, half transform can integrate evidence from all parts of the image to find the dominant line, even if it's or partially obscured or noisy. Okay, so demonstrate robustness to noise. Okay, this particular function I have created. Then I have created a noisy version with different types of gaps. Then I have processed both the images. Okay, then I have found lines using the probabilistic half transform. Then if lines are detected, okay, then I have detected the lines, okay, in this particular function, and then I have displayed the results. Let us see. This is the clean original image. These are the clean edges. Then this is the line detected, which is the cleaner version. Okay. Then this is the noisy image which I have created. I have tried to apply some type of noise. Then within the noise, these are the noisy edges fragmented. Okay, here you can see some amount of edges, but a lot of edges are there. And if you will try to see here, okay, whether you are able to detect this particular line or not, no, you are not able to detect because of the noise. Okay, now this particular noise is mixed with this particular background, and now this particular three white dashes you are unable to visualize. Okay, so it is indeed robustness to noise, but not to the extent but to the extent only when you will try to create some type of hyperparameter tuning. Okay, then only the robustness would be there, the component is there. Okay, if you will use the parameters as they have been given, okay, then in those particular cases you won't be able to distinguish uh, the images in the non-noisy in the noisy background conditions. Okay, this is the thing. Then finding document orientation for these queuing. Okay, when scanning a document, it might be somewhat tilted. Okay, half transform can find the dominant lines, try to automatically correct it. That is already there within your OCR pipelines. Okay, if, even in your CAM scanner, this particular thing is already embedded. You can see here particular function I have created. Then I have tried to find some of the tilted text lines. I have added some noise also and process the image and calculate the dominant angle. Okay, center of the image, and I try to de-skew that. Okay, so if my original document is skewed to 15 degree, okay, these are the edges half input, and after this, if I see here the de-skewed result, okay, which is corrected to 0.00 degree, okay, that is present here. So 15 degree skewness we just have to try to eliminate using the half transform. Yes, it is indeed a powerful demonstration of the half transform. Okay. Next, half accumulator. Okay, if you try to peek inside it, okay, magic of half transform happens in the accumulator array or the parameter space. Each edge pixel votes for all possible lines. That is the combination of rho and theta that could pass through it. Brightest spots in this accumulator correspond to the strongest lines in the image. Okay, let us have to generate this accumulator, and then we have to visualize. Okay, so first of all you have to define the visual half accumulator. Then you have to define the half space parameters, then build the accumulator, then you have to vote, then you have to find the peak in the accumulator, then you have to visualize the image half space and the detected line. Okay, So see here, original image was this one, which was having one diagonal line. Okay, and the half accumulator space, which was based on the voting, as this particular one. Okay, this is the output. Then from the accumulator peak, this particular line we are able to distinguish, but the thing is the length has been slightly extended. Okay, so this is for within an image, you are even able to detect what is the position of this particular line. Okay, using this particular accumulator peak concept. Okay. Final conclusion is this one, that it is robust. Yes, it is robust, but it is subject to some, if huge amount of noise is there, as it was there in demonstration one, then it wouldn't be able to segment, or it wouldn't be able to find a line. Okay, or find a particular image feature. Okay, so it is robust. Yes, it is indeed robust. It is able to detect shape, line, circle, but it is based on your hyperparameter tuning. Okay, so in noisy, incomplete, or occluded images, you have to word the mechanism. Okay, in the parameter space. Okay, key insight is this one, that transform the problem from image space to parameter space, where finding patterns becomes a simpler task of detecting peaks in an accumulator. Okay, trade-offs, you have to always be ready for that, for flexibility in computation cost, as well as the parameter sensitivity. Okay, so these particular one are the practical trade-offs. Real world examples use applications include autonomous vehicles, your industrial automation, your document preprocessing, your medical extraction, medical imaging. Okay, so these are the things. Okay, simple transformations you can try to use. Please, after the class is over, please at least once try to download this particular notebook, try to run it yourself. Thereby, you will get much hands-on idea how to use the concepts which are already being taught in the theory. Okay, in great detail. Yes. Yes. At 1651, you asked one question, sir, in half transform and noisy edges, it seems similarity in images, noisy and half images, similar, is it different? Okay. See here, within the context of this particular transformation, okay, I'll just try to explain you in brief. I think you are talking about demonstration one, because within this only I introduced some noise. Okay. First of all, I created a clean image. Okay. Clean image was there, original image was there. Then within that, clean edge detection is performed and line detected in clean version is already there. But you are talking, when you are talking, yes, the image is same image is there, but I have induced particular noise within that. Okay, so same image is there. I have genuinely tried to induce some type of Gaussian noise, Gaussian blur inside it, in order to evaluate the performance, or uh, in order to evaluate the robustness of my algorithm, I have genuinely induced the noise inside it. This is particularly done in your research, for your research purposes. Okay, because if the algorithm is very able to distinguish between two particular features in noisy conditions, then only it would be much more efficient in context of your practical applications. Okay, that is the thing. These images, this image and this image is almost same, just I have induced noise inside it. And in the similar fashion, this original document is there as is. Here I haven't used the concept of noise, but noise I only introduced in demonstration one. Why I used? Because in order to evaluate the performance of the algorithm. Okay, and increase the practical ability of the algorithm. Okay, that is the thing. You can yourself train some of the models. Okay, if you are a researcher, you can always try to train some of the models. Okay, some of the models you should train, even you are in a UG, you are in a PG or you are PhD for all of these particular courses. Try to train some of the models, try to evaluate the performance of the model. Thereby, you would be getting hands-on experience on the theoretical concepts which are being currently dealt in our theory lectures. This protocol is very simple. Prior to attending this particular session, go through the video lectures, solve the assignments. After that, any doubt is there, then this particular doubt solving sessions, three of the sessions are being hosted. Clear all your doubts so that you can pass the examination with flying colors, as well as you can get the hands-on experience on theoretical as well as practical aspects of the computer vision. Okay. So thank you all. Thank you very much for joining the session. I hope it was a fruitful session. Okay, do join the session next week, same time, same link. Okay. Yes, sir, I am working in images in computer vision as a project by images labeled. Okay, very nice. Please go ahead with it. If any doubt is there, if any confusion is there, then feel free to ask. I'll be more than happy to solve your queries. Okay. Yes. Okay. Thank you. Thank you so much. You can kindly leave if you are not having any doubt. If you are having any doubt, then feel free to ask. Okay. Thank you. Thank you for joining the session. Do join the session next week, same time, same link. Thank you all. Okay. Okay. Thank you. Thank you all for joining the session. I am ending the call for everyone.